Our final project is about the Wilberforce pendulum, and it is a mechanical system invented by Lionel Robert Wilberforce. And this system is has a block attached to a spring, and take the spring as a cylindrical twisted wire. After stretching, the advancement in each turn changes, which results in a rotational and torsional vibration at the end of the spring. And now we're showing the video of the Wilberforce pendulum here. In our project, we'll try to simulate the behavior of the Wilberforce pendulum and investigate how different parameters will affect the motion of the system.
The main component of the Wilberforce pendulum is a cylindrical cross spring with a constant circular cross section. The spring is characterized by the radius r, the pitch diameter d, the head angle alpha, and the number of turns m. The behavior of this spring during the axial and angular displacements is governed by a set of linear equations determined by the constant efficient A, B, C. Using the relevant knowledge of the Newtonian mechanics, we can easily obtain these two formulas. This is a system of linear equations with constant coefficients. This is the subject of our subsequent numerical calculations. Now, the dynamical equations derived from the spring behavior are integrated into Lagrangian mechanics to calculate the resistance of the system. This analysis yields two circular frequencies, omega z and omega theta, as you can see from these places, for the vector and the torsional vibrations respectively. Stable motion occurs when the amplitudes of these vibrations are equal, as we can get from there. So the equivalent mass and ratio and the moment of interior between K1 and K2 are consistent, which is crucial for coupling condition for the Wilberforce pendulum. Additionally, an off-center initial release position is considered, resulting in a system of equations that determine the motion of the pendulum. Is from the basis of subsequent numerical calculations and algorithms developed in the future study.
And during our project, we chose two different methods. The first one is Euler method and Verlet method. And we figure out that we decide to go with the Verlet method because it's more accurate and more stable. Well, in the analysis, we also did a fast Fourier transform, the FFT, which is a part of the NumPy. Now I'll walk through the code. So first we import all the packages that will be used for the coding, and here we are having the initial conditions, and some of the parameters that have actual numbers are taken from the experiment that one of our group mates has done before. During the simulation process, we initially adapt the Euler's method, which is shown here, and then we found that it's compared to for that method, it's not as stable as it, and also it's less accurate. So we decide to go with this for that method here by using the formulas that we talked before, and here are the coding. In this section, we plot the results that we get from the for that method with all the plots. We also perform a fast Fourier transform to better analyze all the data in frequency domain, and it's more intuitive. And now we'll talk about the results that we got from doing the simulation.
It can be found that the experimental results are in good agreement with the calculated results. At the same time, it's easy to notice that there are, at the center of the envelope, there may be a certain deviation between the experimental results and the calculated results. This may be caused by the initial angular displacement being accidentally added during the release. Since the data was recorded for a long time, the error of the initial angular displacement at that time cannot be determined. So we conduct a simple verification below by assuming a small angular displacement and then calculating. We can see these results. Compared to the last one, at this time, it can be found that the calculated result matches almost perfectly with the experimental real data results. We can't help but note that there's some difference between in the envelopes of the two images. Our guess is that the damping, including but not limited to the air resistance, is not simplified proportional to the first power of the speed, but maybe proportional between the first power and the second power of the speed. And now the challenges we are facing.
So in this study, we simulated the Wilberforce pendulum, which shows coupled translational and rotational oscillation using material and Newtonian mechanics. And our numerical solutions reveals that the pendulum's sensitivity to initial conditions and parameters like damping coefficients and spring constant, illustrating complex energy transfers that are relevant for designing similar system in mechanical engineering or robotics. We applied Euler's and Willet's method and decide to go with the Willet method because of increasing stability and accuracy. And we use graphical tools like Fourier transform to analyze the data we got from the simulation. And now we're going through the future directions that we can go with this project.
So now we want to talk about some future directions, and there are three parts of it. So the first one is we really want to create animations to demonstrate the whole process. So we write a code about it, but the result is not very good. So you can see the mouse is just bouncing around at z equals -2, and the spring is very small. So the animation is not very good. And the second one is we want to consider the initial non-zero polar angle phi. So if phi is non-zero, then we only include a kinetic energy term and a potential energy term in the Lagrangian of the system. So we can solve the Euler-Lagrange equations. There are three of them. And we also use the same Verlat method to compute the three functions of displacement and theta and phi. But the result is not very good. So we can see that the displacement the displacement and the angle theta boost up to like 10 to the 6 orders, which is apparently not correct. And phi increases from like 5 degrees to more than 50 radians. So this result doesn't make sense. And we want to see where's going on, but we don't have enough time to do that. And the third part is we want to plot the change in energy conversion rate when the coupling conditions change. So we also write code about it, and we change the value of the mass so that we can control the value of the ratio of the mass to the factor K1. Recall that the perfect coupling condition is the ratio of M over K1 equals the ratio of like K7 over J. But now we only change the mass, and so we expect there's a value of 1 that appears somewhere when mass increases, because at that position the perfect coupling condition is reached, but we don't observe it. Instead, we get a very straight horizontal line. So there's something to fix in the code. Yeah, that's basically the future directions.